So this is the second video in a series where we look at this year's Schweitzer problems and try to solve some of them. I will include links in the video description to the full list of problems, as well as the solution that I'm going to present to you now. So you can open that solution in a separate tab, and you can, or a separate window, and you can look at it while we are going through the solution. So let's look at problem number 2 on the list. So just like the previous problem, problem 1, it involves sequences of numbers, but instead of sequences of natural numbers, now we are going to look at sequences of real numbers. So we have the following statement to prove. It says that if f is a real function which is continuous and periodic, and alpha is an irrational number, then the following sequence of real numbers, which consists of the fractional part of the number n times alpha plus f of n times alpha. So we are taking the fractional part of this number, and n is running through the elements of the set of natural numbers, so 1, 2, 3, and so on. So then this sequence of numbers is dense in the closed interval between 0 and 1. Okay, so again, f is assumed to be a continuous and periodic function. Alpha, this fixed real number, is assumed to be irrational, and our statement is that then the sequence of real numbers is going to be dense in the closed interval 0 to 1. Okay, let me just make a note that these curly brackets again denote the fractional part, taking the fractional part of whatever is inside of them, between them. So the fractional part of x is just x minus the floor function applied to x. So for positive numbers is just x minus its integer part, so whatever is after the decimal point. And for negative functions, you have to add multiples of 1 as so you get inside this interval between 0 and 1. So this is how it's defined. Is the fractional part of x. Okay, so this statement, this problem was set by Vilmos Totik, who is actually the world expert in approximation theory, an area in mathematics, who actually has an Erdős number of 1. So let me just include this. So this was said by Vilmos Totik. I didn't say, but in the previous problem was set by Tamás Czernyák. I will try to include the problem setters in these videos as well, their names. So let's try to solve this problem, prove this statement. So as usual, feel free to pause the video at any point, and if you want, you can try and continue, even complete the proof if you can. So let's look at this these conditions. So first of all, f is periodic. Let's just introduce some notation. So let f have some period. So let's call that period beta. Let beta be a period of the function f. So meaning that f of x plus beta is equal to f of x. So shifting the argument by beta does not change the value of the function, and this is true for all x. Okay, so beta is a period of our periodic function f, and right away we can make a change to this function. Well, introduce a new one, which is, instead of being beta periodic, would be 1 periodic. So we can sort of squish or stretch in the horizontal direction. So we create a 1 periodic function from f. So let me just do that. We see that this unit interval plays an important role in the statement. So we want to create this 1 periodic function instead of having this beta periodic function, but we want to create it from f, using f. Okay, so let's just define a 1 periodic function, define the 1 periodic function which I'll call g. So g of x is defined to be f of beta times x. So I multiply the argument of f by beta, and with that sort of scaling in the horizontal direction, I achieve that this function will have a period of 1. So just to check that, let me just write, let me just calculate what is g of x plus 1. So by definition, that's f of beta times x plus 1. If I expand the argument, the product in the argument, I get f of beta times x plus beta. But now I can use that f is beta periodic for all arguments. So that is the same thing as f of beta times x, which again by definition is just g of x. So this is true for all x's. Now we've seen that indeed this new function g is 1 periodic instead of being beta periodic. And just like f, this scaling in the horizontal direction will not change continuity. So just like f, g is also continuous, also a continuous function. But the good thing about creating this 1 periodic function is that now, due to 1 periodicity, we have the following for g. So for g, if we want to look at a place and the value that g takes at that place, we can just step back into the unit interval by multiples of 1 and go back to the unit interval, basically take the fractional part of whatever number we are looking at the number line and look at the value of g at that fractional part instead of outside of that unit interval. So let me just formulate this or write what I mean. So this implies that g of x is equal to g of the fractional part of x for all x. Okay, again, the argument here is to take this x and use 1 periodicity to if we are not within the unit interval, to step in steps of 1 as many times as we have to, left or right along the number line. So we end up in the unit interval, meaning we end up at the fractional part of x, and we'll get the same value for g at both places. Okay, so that was the trick. So that's the utility of having this one periodic function, because now what we can do is consider, so a consequence of this is that if we look at the sequence of numbers that we are interested in, it's going to be true that n times alpha plus f of n times alpha, well, its fractional part is going to be the same thing. Okay, let me do a bit of manipulation here. So it's going to be the same thing as n times alpha plus g of n times alpha over beta. Okay, so since g of x is defined to be f of beta times x, that means that f of n times alpha will be g of n times alpha divided by beta. So if we want to go back and forth between these functions, if we want to have g of x, we have to multiply the argument of f by beta. If we want to have f of x, we have to divide the argument of g x over beta. So that's what we've been doing here. So take the fractional part of that, and now we can apply one periodicity, and in particular this property of g, to get n times alpha plus g of the fractional part of n times alpha over beta. Okay, and take the fractional part of that. So this is going to hold true for all natural numbers n. Okay, so the point is that now we can look at this sequence of these numbers, where again alpha was an irrational number. So we are taking n times alpha, multiplying alpha by n, and then adding to it g of the fractional part of n times alpha over beta. Okay, and take the fractional part of this expression. So let's distinguish two cases, because there are two possibilities, two ways to continue. So the reason I'm saying that is because we are looking at this unit interval 0 to 1 with alpha being irrational, and you might recall that if you take the multiples of an irrational number and take the fractional part of that, now that will form a dense subset of the unit interval. Okay, so the fractional part of multiples of an irrational number will always form a dense set in the unit interval. And what we have here as a statement is actually a generalization of that, because f, this continuous periodic function, could be set to 0, the 0 function, and then we end up with that result that I just said, that the fractional part of multiples of an irrational number will form a dense set of the unit interval. Okay, so it is very important that alpha is irrational. Now the next question is the relation of alpha to this period beta. Okay, that is obviously going to play some role, and basically what we see here is multiples of this irrational number and multiples of alpha over beta. So their relationship is important in this setting. So that's why we have two cases to distinguish. In the first case, let me just say, so there are two cases. So the first possibility is that the numbers 1, alpha, and alpha over beta are rationally independent. Okay, meaning, so rationally independent means that the only way I can take 3 integers and form this linear combination of p times 1 plus q times alpha times plus r times alpha over beta equals 0 with integers. P, Q, and R integers. So if this happens, I can connect the number 1 and alpha over beta in this way using integers, then all of them must be 0. So basically only this obvious way of writing or getting 0 is possible where I just multiply each number by 0. No non-obvious or non-trivial way of connecting them exists. Okay, so that is what we mean by rationally independent. So that's the first possibility we have to look at. So let me clear the board and then we'll look at this first possibility. Okay, so let me just quickly say what we are trying to prove. So we are trying to prove that if we have this irrational number alpha, we take it, multiply it by n, and then add to it some continuous periodic function at n times alpha, take the fractional part of this sum, and consider the sequence as n go through the natural numbers, and it's going to be form a dense subset in the unit interval. And we arrived at 2 possibilities. So we said there are 2 cases to distinguish. Okay, so the first one was the case when we have 1 alpha and alpha over beta rationally independent. And I have just told you what rationally independent means, that there are no non-trivial linear combinations of these numbers with integer coefficients giving you 0. So if they are rationally independent, that means that then the sequence of points having coordinates and the fractional having coordinates, the first coordinate being the fractional part of n times alpha, and the second coordinate being the fractional part of n times alpha over beta. Then this sequence of points, as n goes through the natural numbers, is going to be dense in the unit square. Is dense in the unit square. So I'm actually using the statement that says that if I have the fractional part of multiples of an irrational number, it's going to give me a dense subset of the unit interval. So I'm using it in both coordinates in this case. Okay, so it's going to be give me a dense subset of the unit square. And now, but that means, of course, that I can choose any x. So what I didn't tell you what a dense subset is, but intuitively, hopefully you have some sort of understanding of this. So dense means that points in this subset get arbitrarily close to whatever is the larger set, to points of this larger set, meaning that I can choose a subsequence of this sequence that gets close to any previously fixed point in the set that I'm looking at, in which we have this dense subset. Okay, so I'm saying that since we have this dense sequence in the unit square, we can choose an arbitrary x. So for any number between 0 and 1, so for any x in the open interval between 0 and 1, there is a subsequence of a sequence of natural numbers. So I'm denoting these natural numbers, these indices, by nk. So this is a subsequence of the set of natural numbers, such that the limit of these points along this subsequence so we are taking these points with first coordinate being the fractional part of n times alpha, the second coordinate being the fractional part of n times alpha over beta, but we take these points, a subsequence of these points specified by this subsequence of natural numbers. So we can find a subsequence such that the limit of these points is the point with coordinates x and a half. Okay, so this is, again, because we have this dense set of points in the unit square. For any number between 0 and 1, we can find a subsequence of the first coordinates so that they converge to x, and for any and for 1/2 we can find a subsequence of those coordinates that they converge to a half. Okay. Next, we can now use that our function f is continuous, so it will behave nicely if we interchange applying the function and applying the limit. So since f and in fact this function that we created from f, that is one periodic, they are continuous, so since they are continuous, the limit of these functions of points that we are interested in along this subsequence will have the following form. So nk times alpha plus f of nk times alpha, taking the fractional part as k goes to infinity. Now, of course, this was equal to the fractional part of nk times alpha plus g of nk times alpha over beta. So this is just rescaling as k goes to infinity. But of course, because g was one periodic, this could be written as the limit of the fractional part of nk times alpha plus g of the fractional part of nk times alpha over beta, okay, as k goes to infinity. And now we can use that g is continuous, meaning that if these coordinates go to x and 1/2 respectively, then the limit of this expression will be x plus g of 1/2. Well, we should take the fractional part of that, but it goes to this number. Okay, and since x was an arbitrarily chosen number on the unit interval, this means that this number can actually result in this expression x plus g of 1/2 fractional part can result in any number that we want to. Okay, so that's an important thing. This is just a constant added to x. Taking the fractional part shouldn't make any difference. Okay, so since x was chosen arbitrarily, we can actually find a subsequence of this sequence of numbers such that we converge to that previously fixed number on the unit interval. This is what it means to be dense. For this sequence to be a dense subset of the unit interval. Okay, so that's the first case. That's the case when these numbers, this irrational number alpha, and the ratio of alpha and the period of f were rationally independent. That case is covered here, so we can just say that, let me just finish off by saying that the number x was chosen arbitrarily, hence the statement follows. Well, for the first case, what about the second case? So what about the case when these numbers are not rationally independent, but rationally dependent? So if 1 alpha and alpha over beta are rationally dependent, remember, that means that there is a non-trivial linear combination of these three numbers with integer coefficients such that we get 0. So let me just say that again, that if they are rationally dependent, that means that there are integers, let's call them p, q, and r, not all 0, such that we have this linear combination of p times 1 plus q times alpha plus r times alpha over beta being equal to 0. Okay, so this is what it means to be rationally dependent. So next, we can use that alpha is irrational. So this coefficient r, the integer r, cannot be 0, since if it was 0, then alpha could be expressed as the ratio of two integers, but alpha is an irrational number, so it cannot be expressed as the ratio of two integers. So r must be non-zero, okay? So since alpha is irrational, r cannot be 0. So, okay, r must be non-zero, that's important. And next, since we have this relation between the three numbers, alpha is not 0, so it's either positive or negative, it's an integer. So if it were negative, we could multiply the whole equation by 1, so both sides by -1. So flip the signs of each of these, of all of these coefficients. So we can always assume that r is in fact positive. So we can assume that r is an integer that is greater than or equal to 1. Because if it would be negative, we could flip all of the signs of these coefficients. So if not, flip signs is what we can say here. And then we can move on to now fix again some number between 0 and 1 and try to argue that again there will be a subsequence of those numbers which tend to that number. So let me just clear the board and we can finish this proof. Okay, so to finish the proof, we just fix a number, an arbitrary x between 0 and 1. So fix an arbitrary x between 0 and 1. And since alpha is still irrational, that number is still irrational, there must be a subsequence of the natural numbers such that the elements of that sequence times alpha, when taken the fractional part of this subsequence, will converge to this number x. So there is a subsequence of the set of the sequence of natural numbers such that the limit of the fractional part of nk times alpha as k goes to infinity will be this x. Okay, and since our functions f and the g that we created from it are continuous, we can do the following, just like something we did in the first case. So since f and g are continuous functions, we have the following. We have the following limit. If we take again the limit of that sequence of this expression along this subsequence, we will get the following. So the limit of the fractional part of nk times alpha plus f of nk times alpha as k goes to infinity. So this fractional part can be rewritten using the function g instead of f. So that just means rescaling by beta, by the period of f. So this is the same thing as the fractional part of mk times alpha plus g of nk times alpha over beta. Okay, of course the limit is still taken as k goes to infinity. And now we can express alpha over beta over here. Oh, I forgot to do something. So what I wanted to do, instead of just considering this subsequence, is multiply each of these expressions by r. So at this point, you see that there's alpha over beta here, and here I have this relation between 1 alpha and alpha over beta, but that is multiplied by r, and I want to use that. So let me just make a correction here. I want this multiple of r in there, but of course, if I want to have want to be consistent, I should have a multiple of r over there, and a multiple of r over there, multiple of r over there. So if I insert those factors of r, now I can say that we have r times alpha over beta times n sub k, and now r times alpha over beta can be expressed as minus p minus q times alpha. Okay, if I just rearrange this relation. So what I get is the limit of the fractional parts as k goes to infinity of n k times r alpha plus g of nk minus nk times p minus nk times q alpha. Okay, so that is just minus nk times p minus nk times q times alpha, which I got from rearranging this relation and expressing r times alpha over beta. Okay, so that is still correct. And then we can use the fact that that G is one periodic. So at this point, we still have the fractional part of n sub k times r times alpha plus, now we have G of, well, here we have a negative, well, perhaps positive integer, but an integer nonetheless, which can be omitted because alpha is one periodic. So we can take steps, unit steps, and not change the value of G. So this is equal to G of minus just n sub k times q alpha. Okay, so that was our goal here, is to have n times k times alpha, n sub k times alpha in both arguments, because now we can use that G is continuous because f was continuous, and this limit turns out to be the fractional part of r times x, right? Because n sub k times alpha tends to x, so r times that tends to r times x, plus G of minus q times x. And we have to take the fractional part. Okay, again, because n sub k times alpha converge to x, and g is a continuous function, so it can be interchanged with taking the limit. Okay, so this is what we got. We got the fractional part of r times x plus g of minus q times x. Okay, this expression, so let me just introduce a new notation for this expression inside the fractional part. So if I just say that we have this function, the function h of x defined to be r times x plus g of minus q times x. Okay, this function depends on, so it takes x, which was an arbitrarily chosen number between 0 and 1, and spits out r times x plus g of minus q times x. Since g was continuous, this function will still be continuous, and it's actually continuous on the closed unit interval 0 to 1. Okay, so it can be extended to the closed interval between 0 and 1. And in fact, what we can show, that just by thinking a bit, that the value of h at the different ends of this interval differ by more than 1. Okay, that is very important. So h1 is of course equal to r plus g of minus q, okay, which is now, notice that it's an integer, so that's the same thing because of the one periodicity of g as r times g of 0, okay, because we can shift this step by step, unit by unit steps to 0, so it's the one periodicity. But of course, r, we found that it should be greater than or equal to 1, meaning that this expression r plus g0, g of 0 is greater than or equal to 1 plus g of 0. But of course, 1 plus g of 0 is the same thing as h0. Okay, why is that true? So, well, sorry. So if I take h0, I get 0 plus g of 0. So this is 1 plus h of 0. So that was the point. We have at different ends of this interval, we have these two values of h differing by at least 1. Okay, so we have a continuous function h on the closed unit interval whose values at the endpoints differ by more than 1, meaning that if I take the fractional part of, because this is the fractional part of h of x, I will cover the unit interval 0 to 1. Okay, so let me, and this concludes the proof basically, because this means with the continuity of h that the range of h includes the unit interval, that the range of h contains as a subset the unit interval. Okay, and well, the range of not h, but the fractional part of h contains the unit interval, because we are taking the fractional part. And remember, the limit that we started with, the limit of a subsequence of our original sequence, resulted in this number, which, if x runs through from 0 to 1, the real numbers between 0 and 1, we will in the end cover the entire unit interval. Okay, so this is the end of the proof. This proves that indeed there is a subsequence for any numbers between 0 and 1, there is a subsequence of that sequence which converges to that number previously fixed between 0 and 1. So this is the end of the proof. So let me just draw a quick diagram or help you with this last point. So if I have this function h, what the point was here is that if I have 0 to 1 over here, and let's say here is my h0, then h1, the value of h at 1, should be greater than or equal to 1 plus h0. So I'm adding 1 plus potentially a bit to get up to h1. So and this function should be continuous. So it starts out from 0 at 0 being h0 and at 1 being h1. And this is some continuous function. Okay, so when I do take the fractional part of this expression, I will have to chop it off at 1, shift it down by 1. But the point is that somehow this will basically cover the unit interval as its range. Okay, so I'm not sure if this is perfect, this diagram, but this is the idea behind the last part of this proof. All right, I hope you enjoyed solving this problem, and I'll see you in the next video.